This is a workshop called God in the New Physics that was given at the Spiritual Life Center in Wichita, Kansas on August 6, 1996. The day before it began, the participants were given several pages of quotes on modern science to read. Here are some samples. The first passage comes from a Discover magazine article on the work of the physicist Alexander Vilenkin. Since cosmologists were already using some of the tools of quantum mechanics, Vilenkin reasoned, why not borrow another of its tricks? According to quantum mechanics, the emptiest possible void of outer space is never really completely empty. It is filled with tiny particles of matter that are always popping into existence and then, an instant later, popping out again. If a particle can pop into existence from nothing, why not a whole universe, Vilenkin wondered. In a stroke, he reduced creation from a metaphysical event to a physical one. What had seemed unknowable was suddenly reduced to a set of equations. Another quote came from Stephen Hawking's book, Black Holes and Baby Universes. This article is not about whether I believe in God. Instead, I will discuss my approach to how one can understand the universe. What is the status and meaning of a grand unified theory, a theory of everything? There is a real problem here. The people who ought to study and argue such questions, the philosophers, have mostly not had enough mathematical background to keep up with modern developments in theoretical physics. And a third quote came from Frank Tipler's The Physics of Immortality. Either theology is pure nonsense, a subject with no content, or else theology must ultimately become a branch of physics. The reason is simple. The universe is defined to be the totality of all that exists, the totality of reality. Thus, by definition, if God exists, he, she, is either the universe or part of it. The goal of physics is understanding the ultimate nature of reality. If God is real, physicists will eventually find him, her. These quotes ended with the question, if theology has to be built on the foundation of cosmology, then how would you develop a new theology based on the new cosmology? There was no other explanation given. What is your answer to this question?
After they gave out those pages, that you weren't intimidated, and I thought a word to the wise would have been sufficient, and you would have gone and done something else. But since you're here, we're going to go ahead and do this. And if anything goes wrong, we're going to blame it on Philip because he's the one who invented this topic. So I don't know why he did it, and I don't know why he gave it to me, but that's what we'll do. Now, Sister Carmen tells me she has to leave early, and she's going to the dentist. So that gives you some idea that if she'd go to the dentist rather than stay here, how painful this is going to be. So I want you to be prepared. We have, let's see, I want you to break down into small groups, let's say about 5 people in each one. So we'll take the first 5 here, or first 5 or so here, and so forth. And we could have maybe 4 different little groups. I want you to come up with one idea of what the new theology should be like based on the new cosmology. Because if we don't make an effort to kind of get into it personally, then it's just going to be remain a bunch of words to it.
We have more questions than answers. I don't think we have any answers. We have only questions. But anyway, from looking at this material, It seems like instead of the universe being a determined thing, the universe is a machine, as absolute. It's now chaotic, spontaneous, and it's free. There's some freedom there that didn't seem to exist under the Newtonian idea. It's a mystery rather than a machine. And it seems like it's evolving rather than fixed. So we thought about maybe a theology that was also evolving or was open somehow. Don't know what it means to say that, except to say that that would reflect the universe. Prayer is a kind of energy that can be utilized by for others and together. Since the earth is would be thought of as a living organism, the universe is also a living organism. And then rituals, our mass is sort of like a machine, like our universe is. It's all fixed and written down. What would it mean for our ritual to reflect the new idea of the universe? Would that mean a spontaneous mass, whatever that is? I don't know what that means, but I don't know. And then we didn't talk about this, but I wrote it down last night, just in thinking about it. If the universe is evolving, is the body of Christ also evolving, and is the body of Christ cosmic too?
Great. Very good. We ready for our first group here?
I'm not really sure what you're looking for, but I can just give you my own personal beliefs. I believe that we're all connected with energy and with one another throughout the world. I believe the same energy that moves the clouds in the sky is the same energy that we have, and it moves us. And because of this connectedness, I feel like this encompasses our universe, and I believe there's other universe out in the atmosphere.
Great. Very good.
Basically, we think that everything that's been said thus far is absolutely wrong, and what I'm going to say is wrong too. So I mean, doesn't matter. I'll just throw a few balls up in the air that we were talking about. One is looking at historically, looking at through history as different ages with different degrees and levels of ability to observe the universe comes up with its own cosmology. And as we look back historically over it, we see, well, that's pretty quaint, you know. And perhaps we should begin with the assumption that what we're coming up with today is going to look pretty quaint 100 years from now as well. So not get too proud of it. On the other hand, there's, I think, a large portion of the scientific community who thinks that we are narrowing in on an absolute description of what is in the physical universe. And we're getting down to, description of basic elements and looking for a unified field theorem that works, and that would be the end of science when we do that. And the beginning of what? I don't know. And so is that, kind of hubris, or is that real? Is it possible for us to do that? And if we can, that makes us kind of like, pretty close to God, I guess. And then we have the other phenomena, as we have evidence of, there have been scientific discoveries that have depended upon almost kind of quasi-mystical sort of things, people having intuitions, and Einstein's thought experiments. You have Niels Bohr's having a dream about the structure of the atom, and the guys who did the DNA structure got that through a dream, I guess. And so you have these phenomena going on. So maybe there's between religion and religious symbols, and I don't know if she's left, brought up the symbol of the Taoist symbol, the yin-yang symbol. and as perhaps a description of things that are going on, like in the first paragraph, they're describing energy that is on average zero, because every once in a while matter comes into being, there's positive energy of existence, then maybe there must be something like negative existence. And scientists are talking about, 14 dimensions, 18 dimensions, things beyond our grasp, and alternative universes at any given point in time splitting off. All these are possible, but we can't comprehend them. So, what do we make of that, and how do we theologize about that? And it comes down basically to someone says, a sense of wonder about what is, and how do you give description to that? And then the whole question of what do we do with Scripture with all this, too? Is that become do religious beliefs become tools for physicists and scientists to give explanation and to be used as vehicles to go further into trying to discover the universe and what is? And then there's the whole thing with the Olympics and Dorothy Hamill and the beehive and the flat top and all those other cosmological things. And we got off track somewhere. I don't know.
Now, I think this is a good illustration of your basic kind dispositions. By reading these passages, if you derive what you did from them, it's a matter of being kindly disposed towards the authors. I am not going to be as kindly disposed, so I'm going to take the other side. So if you're kind of taking the positive side and finding the good, I'm going to play the devil's advocate, okay? Let's go to our little thing where if theology has to be built on the foundation of cosmology, how would you develop a new theology based on the new cosmology? Well, was anyone struck by that little syllogism, that little line of reasoning? Do you believe that is true? But I think that if this statement is wrong, and it's based on all these passages, then I think we should look at these passages in a more critical way and see whether they are correct or not. Okay? What I'm saying is that we simply have to develop a certain kind of critical attitude, because I know that now that we're having a lot of things going around about the new cosmology, which is fine, and the things that you came up and presented are kind of the basic good insights that can be drawn from there. But I want to go a step further than that, and I want you to realize that if you simply take what the cosmologists have to say, you're going to have a lot of headaches. And these passages are filled with headaches for any kind of Christian understanding of things. All right? And I'll go through a few examples and try to draw that out. Let's see. We'll take the first one about the Lenkin and the universe, the little particles popping in and out of nothing. Okay? And then the whole universe, well, maybe the whole universe pops out of nothing. Well, that's great. Physicists love to do this because it's kind of a game, all right? Highly mathematized in imagery, and it doesn't cost anything to play that game. So they play the game. And so they will come up with this. But to imagine that this is a statement of the way the universe actually is in itself, there's no grounds for believing it. There's no grounds to believe that particles pop out of true nothingness, or that the universe popped out of nothingness. Okay, that's sort of like going to your bank account and telling your the cashier that You believe you now have all sorts of money in your account because it popped in there, okay? You will not get very far, okay? This is no better from a purely philosophical or theological point of view. It doesn't make any sense, okay? It makes a sense to the physicist, but only if we understand the context that the physicist is working in. For example, their kind of nothing has to do with this cosmic background, which is like an infant. They imagine it sometimes as an infinitely rich energy field. And therefore, from this field, particles may emerge and then submerge themselves. But this is not what we're saying if we say, well, God created the universe out of nothing. These are not equivalent statements. And so, if we were to say, well, we no longer need God as the creator because the universe can pop out of nothing, we have a theological problem based on what some physicist is doing. You would have to ask yourself, are we saying that God is equated with the physical universe, kind of a pantheism, okay? And as Christians, we usually have avoided saying that. Certainly the universe, if it's created by God, is intimately connected with God, but we don't say that God is the universe. Which brings us to one of the other passages by a well-known physicist who was also, I believe, talked at one of the seminars held under the auspices of the Vatican about some of these issues. This is Frank Tipler. He's on page 3 in the middle. Either theology is pure nonsense, a subject with no content, or else theology must ultimately become a branch of physics. The reason is simple. The universe is defined to be the totality of all that exists, the totality of reality. Thus, by definition, if God exists, he, she is either the universe or part of it. The goal of physics is understanding the ultimate nature of reality. If God is real, physicists will eventually find him, her. Well, comment on that. Who's going to comment on that statement? This man is a reputable, well-known physicist. Does the universe have to exist? If it were an intrinsic part of God, it would have to exist. Is that what we say as Christians? From a Christian point of view, our traditional way of thinking does not demand that the universe exists. God freely creates the universe. So that is really, that's one part that simply we would not agree with what Frank Tipler is saying. Okay? He's saying that really God is a part of the universe, or is the universe, and so we're discovering the universe, we discover God. But the reasoning is false from another perspective. Physics is trying to do one thing, and theology is doing another. And it isn't as if physics, theology just takes over where physics fails, because that's a pretty reductive view of theology. It's better, I think, to think that there's more than one way of knowing things. Physics is a very distinctive kind of way of knowing things, based on certain sensible facts that are then subject to the rule of mathematics. But we believe that philosophy or theology are other ways of knowing. For example, philosophy should be able to know the universe in its own distinctive way. We can't expect the physicists to immediately agree with that point of view. They don't know much about that. And so when Frank Tipler is saying either theology is pure nonsense, a subject with no content, or else theology must ultimately become a branch of physics, what he's doing is allowing physics to gobble up everything else, so there's only physics. This is an important point. Even someone like Stephen Hawking is saying some things that we simply can't kind of suspend our critical faculties about. I say, well, here's Stephen Hawking. He should know about the universe. It's not that simple, okay? Let's go and look what he said. We have a quote from him. Okay, here's a good one at the beginning on page 3 under theology, and he's introducing one of his articles. He says it's not about whether he believes in God, and he's discussing an approach about the theory of everything. But he says there's a real problem here. The people who ought to study and argue such questions, the philosophers, have mostly not had enough mathematical background to keep up with modern developments in theoretical physics. What is he saying? What is he really saying there? Right. You have to do it our way, and so therefore philosophers don't have anything to say because they're not theoretical physicists. And therefore they don't understand the math of theoretical physics. One of the things you did say was it's sort of like the physicists are seeking an absolute description of the universe. Am I right in quoting that way? This, I think, is a really tough issue, but an important one, because physics is not theology, okay? You could, or put it, physics is not philosophy, is another way of saying the same thing. It's possible to know things about the universe through mathematical physics. Everybody grants that, okay? And everybody is enamored because you can look at the, seems so sure and real. But it's also possible to know something about the universe through philosophy and through theology, okay? And I don't think you ultimately can reduce one to the other, because it's sort of like being in school and there's mathematics, and so then we look at geography and we say, well, we want to make mathematics take over geometry, so we have a mathematized geography. That would be a hard thing to do. You just go about it a different way. There's different kinds of knowing. And this is what is running through these things. There's a certain confusion going on. Stephen Hawking is talking about theoretical physics, and he is insinuating that that is the way of knowing the universe, and everybody else either may think they know about it and really don't, because they can't follow what's really going on. It's only him and a couple other guys can do that. He says that in the other quote. I'm not making it up. But this is a problem, okay? Because basically it's not true. The church, at a certain point in time, was very reactionary because it was the emergence of science, like in the 16th century, in Galileo, and the whole emergence of science as having its own method. Before that, science was never separated from what was known as natural philosophy, and it was taught in a kind of philosophical way. And even people like Newton would call themselves natural philosophers. It wasn't separated out. But at that time in history, it began to separate because the method of physics, for example, is a very distinctive method, okay? Once the church saw this happening, it reacted in a very poor fashion and tried to kind of coerce and, bamboozle the physicists and not let them do their thing. Eventually, it was like a long marriage breaking up, going into a bitter divorce, and that has gone on until today. All right, so we don't want to get into that science-bashing thing. On the other hand, the scientists, in retaliation, have gone ahead, and what they've done is sort of say, well, this was prevalent in the 19th century particularly. They had a certain arrogance that we are the people who know everything, and all this other kind of stuff, philosophy, religion, and all, is outmoded and just the remnants of past superstition. That's no way to have a dialogue either. What you need are physicists on one hand who have a sense of philosophy and theology, philosophers and theologians who have a sense of physics talking to each other. And we're going to look at some of this same kind of back and forth. But in the meantime, when you pick up the news magazine, or you pick up the science magazine, or you hear these kinds of popular presentations, the only point I want you to take away from this first session is simply think about it. Because once you think about it, then you say, oh, yeah, like you're doing. But you have to be critical, because there's a lot of just loose kind of talk going on. And that doesn't help us. You can't, take this stuff as some kind of new gospel, the new cosmology, even the new story, as if it's replacing the old one. And, here we are, poor benighted Christians, running around trying to figure out what the latest cosmology is so we can bring our theology up to date. That doesn't work that way. Physicists have some very interesting things to say, okay? And we're going to look at one of them. But they say it wrapped up in such a package that it's a very difficult and delicate job to unwrap that package and see exactly the import of what they're saying. This is particularly true in quantum mechanics, the science, this sort of the knowledge of the very small. Science that once looked at the universe as a piece of clockwork, as someone mentioned during these presentations, at the beginning of the 20th century underwent all these shocks, okay? One of the shocks was relativity. But perhaps an even bigger shock was quantum mechanics that developed in the first years of the century, okay? So that this has created very interesting questions that are not solved yet. You can't, like I said, take some of these things about the, if anyone read the thing about the cat, okay? Schrodinger's cat in the capsule, and the physicists are saying, well, he's not alive and he's not dead, okay? Well, Schrodinger, who was one of the developers of quantum theory, he made that example because he objected to what the current understanding of quantum theory was. He was trying to reduce it to absurdity so people would say, oh my goodness, we're being taken for a ride. But when it's being presented in these popular presentations, they're not telling you that. They're presenting it like, get your thinking in line, ladies and gentlemen, and see that this is the new, brave new world we're entering. Well, are we? Okay, are we? Is that true? The cat is both alive and dead in the capsule until we look in there and then it decides which one it is. Is that true? It defies common sense. That's not the best argument, but it is a good one. Just because someone is saying it like this, don't be bamboozled and think that you somehow have to realign your whole worldview. First, you got to figure out whether it's true or not. And that's basically my point for this first time. Let me give you an overview for the rest of the day for those who are brave enough to continue. We're going to talk about quantum mechanics in the second presentation. And then after we talk about quantum mechanics and the third presentation, we're going to talk about what the physicists call non-locality. Okay? And that is a very interesting result that has come up in modern physics and worthy of the attention of all of us to get a little sense of what non-locality means. It means the strange interconnectedness that the universe is manifesting in a way that defies the basic understanding they have of physics. So they're up against one of the frontiers of physics when they're dealing with non-locality. Okay, so those are the two things that are coming. But I want you to continue to participate, and we're going to leave the chairs like this, because if you don't kind of say, well, is that true or not, or question it, or raise some issues as we do this, then we're just going to be back into the kind of passivity that's not good for us. All right? As Christians, we have intellect, we have minds that are really thirsty to know as much as we can. So on one hand, in our professional lives, in our family lives, we are constantly dealing with tough issues and dealing with them as adults. And when we come to the field of our own Christian faith, sometimes our education is not what it should be. You can blame part of it because of the church structures and so forth, but it's not what it should be. We don't have the education we should, and that should be one of our goals in this whole kind of renewal of the church. It's sort of like God has created this marvelous universe, and he wants us to know about it. And how are we going to know? We're not going to find it in divine revelation, because that's not the issue that divine revelation is interested in. But we have the ability to know, for those who are interested, because we have brains, we have intellects. And that's what the physicists are doing. There's no other way we're going to learn about this intimate structure of the universe in precisely the same way. It's like there isn't like, the physicists are looking at this universe and they're seeing a certain face of it. And it's a very fascinating face. My real point, I don't want to knock that at all. It's exciting, except we have to realize how they're going about it. If we realize what their method is, then we'll understand what their results are and how they apply to the rest of us. All right, we're going to talk about quantum mechanics, quantum theory this afternoon. So this is simply the way the physicists try to deal with the very small, the subnuclear particles, the nature of matter. Okay? Now, when the 20th century opened, physicists thought they had a pretty good lock on what was happening. They had a certain view of the universe. You could call it a Newtonian view of the universe, because you had Newton's laws of motion, and you had all these discoveries. And so they said, well, we're pretty well organized. And some physicists actually felt, well, we're at the end of, approaching the end of physics, and try to fill in the details. Well, in 1900 in Berlin, a physicist named Max Planck is doing an experiment, and he has this metal tube, black metal tube with a hole in it, and radiation is coming out of it. And they call it black body radiation. And anyway, the radiation is coming out of it, and he's measuring it. And as he measures it, he discovers that it's not sort of coming out in a smooth way as he would expect, but it's coming out in sort of clumps. So he calls them quanta. Well, we won't really get into that, but that was the, why would it happen like that? He didn't know. And he tries to devise a formula to explain that the fact that this matter is not appearing like anticipated. A few years later, in Bern, in Switzerland, so now it's 1905, this obscure patent examiner writes 3 papers for this famous physics journal, one of the papers is on the special theory of relativity. Another is on what is called Brownian motion, which is they had observed that tiny little particles, like on the surface of water, would jiggle around, and they couldn't understand why these tiny little grains of pollen or whatever they were would jiggle around. And the third paper was on something called the photoelectric effect, where Einstein ended up, it's Einstein we're talking about, Einstein ended up relating this photoelectric effect to some of the ideas of Planck. This is all just details that we don't really need to go into, but the important point is simply that these, what look like anomalies, are showing up in physics. And over the next 20 to 30 years, physicists are going to make this tremendous effort to put all these things together. And in the 1920s, this process reaches the zenith from a mathematical point of view. And from different directions, different physicists are creating a mathematical theory that will explain all these events that are happening in the micro world. And that's what they call quantum theory. Okay. And they agreed on this mathematical formulation. They could see that this explained the different phenomena they were seeing. However, and this is where it gets more difficult, there were two different attitudes about this mathematical formulation. One attitude was the mathematics is kind of getting pretty close to what we can know, and we can't really know what things are like in themselves. It's sort of what the mathematics tells us. And the other attitude was more of an attitude, we want to know what things are like, more like things are like in themselves. This same mathematical theory is getting interpreted in two different ways. One we could call a realistic way. People like Einstein are not happy with this other interpretation, which we're going to see a little about, which gradually coalesces and has a different philosophical view. But in most people's minds, this other interpretation that eventually went under the name of the Copenhagen interpretation because of Niels Bohr, who was a Danish physicist, this interpretation, both the mathematics and the philosophical interpretation, sort of coalesced and went together, and that is still pretty much the predominant way people view quantum theory. Now, this sounds very abstract, but there's a way we can get at it in more detail. Richard Feynman, who was a brilliant U.S. physicist, once said that the whole strangeness or weirdness of quantum mechanics can be summed up in the two-slit experiment. And that's what we're going to see, what the two-slit experiment is. Before we get into that, one of the things you might have heard about is that Heisenberg, Werner Heisenberg, a physicist, had, as part of this Copenhagen theory, had developed what he calls his uncertainty principle. And that meant that if you were to take an electron and you were to try to measure it, there would be like two dimensions to your measurement. Okay, you could determine its position and its momentum. But the more you would determine its position, the less you were able to determine its momentum. And the more you would determine its momentum, the less precisely you would be able to fix its position. That's why he called it the uncertainty principle. Now, some people thought that this uncertainty principle came from the fact that it was just too difficult to measure these very small quantities, and you're getting in there and you're trying to measure the electron, and it kind of jiggles around because you have to use something to measure it, and you're displacing the electron with whatever you're using to measure it. Other people thought that there was something in nature itself that resisted measurement. Okay, so you have, again, these two different kinds of interpretations. Now, I'm going to hope that this will become clearer as we talk about the two-slit experiment. Let's imagine that there's a screen. And in front of the screen is a barrier, and it has two slits in it, which are these little breaks in the line. And there's a source up here. Let's call it light. Okay? Now, if we take the light and shine it at the barrier, and there is one slit here, what's going to appear on the screen? What will appear? Yeah, or it's a dot if it were just a hole, or a line if it were a long slit. Okay, so what you'd get was some kind of, let's say if you were looking at it sideways, you'd get some sort of line. And if we close this one and let the light go through this slit, we're going to get another line, okay? I can't really draw it here because it would, but, all right, so you get a line. Now, when you shine the light and you leave both slits open, what happens? Speak. Somebody say. You get two lines. Do you? Okay. We would imagine, sort of intuitively, we'd get two lines because the light's going through and you're making two lines. All right? But we don't get two lines. What we get instead is a series of light and black lines, okay, which is an interference pattern. Because what went through here, okay, the light that went through here and the light that went through here, they have created this pattern which indicates that light is in the form of waves, all right? So this was a very common kind of experiment. The waves interfere. Remember if you throw a rock in the pond and there's these waves coming, and if you threw another rock, then when the two waves would meet, some of the waves would reinforce each other and you'd have a big wave. Some of them would cancel out each other and you'd have this lack of a wave. It's the same thing with light. So you can get a fringe pattern or an interference pattern if you send the light through the two slits. Okay, that was just basic physics that everybody knew. But once they started examining this question, they said, okay, what's going to happen if we send an electron through instead of light waves? So let's imagine, we'll do it again. Okay, so we have the same screen. This time we can imagine it's fluorescent or something that when the electron hits it makes a mark or lights it up or whatever. All right? And here's our two slits again, and here's our gun that shoots out electrons. Okay, the electron, we close this slit and we send out the electron. Here's the electron, and here it goes. And it goes through here. What happens? What's going to appear on the screen? A dot or a line if we're shooting a whole stream of them. So it's sort of like the light experiment. Okay? We shoot the electron out and we close this one, we're going to get another line. Now, what happens when we open both of them up? Now here's the thing. What happens? Yeah, you get a wave pattern instead of two lines. So what inference do we draw from that? Okay. Now we're picturing the electron as a particle, as a little particle that's going through. But somehow, if we leave this one open, we begin to get some kind of interference pattern. And so this is the beginning of what they're going to call the quantum strangeness or weirdness. Because how could that work out that way? In fact, because we know the electron is going to go either through this slit and end up here, or it's going to go through that slit and end up here. So how can it form an interference pattern? In fact, if we were to slow down the electrons and shoot one at a time, okay, so it had the time to go through here and end up here, or go through there and end up there. Anybody ever guessed what would happen if we shoot electrons one at a time through the slits? We'd get the interference pattern again, even if they were shooting them one at a time. So physicists began to think about this and said, this is kind of strange, all right? Now, and so they tried an experiment, and they would close one of the slits with the reasoning that if they close the slit and the electron is going through this slit, it shouldn't make any difference anyway. Why should the slit need to be open if the electron's going through the other slit? So they close the slit, and the interference pattern disappears. Okay? Now, I'm going to read you a couple of passages of the kind of reasoning they began to develop to explain what was going on. So really the heart of it is trying to explain how the particles can form a wave. The Copenhagen interpretation is one slit or the other. But then we should not get a wave. Further, if the electron goes through one or the other slit, it should not matter if the one it is. In fact, if we close it, we don't get the interference pattern. Now, a physicist named, I'm going to read a couple of passages from contemporary physicists who have tried to explain this as there is no meaning to the objective existence of an electron at some point in space, for example, at one of the actual observation. The electron seems to spring into existence as a real object only when we observe it. Okay, what are they saying? In fact, let me read this longer passage. The electrons not only know whether or not both holes are open, or both slits, they know whether or not we are watching them, and they adjust their behavior accordingly. There is no clear example of the interaction of the observer with the experiment. When we try to look at the spread out electron wave, okay, it collapses into a definite particle. But when we are not looking, it keeps its options open. In terms of Born's probabilities, the electron is being forced by our measurement to choose one course of action out of an array of possibilities. There is a certain probability that it could go through one hole and an equivalent probability that it may go through the other. Probability interference produces the diffraction pattern at our detector. When we detect the electron, though it can only be in one place, and that changes the probability pattern for its future behavior for that electron. It is now certain which hole it went through, but unless someone looks, nature herself does not know which hole the electron is going through. What is he trying to say? He's saying that if we look at this picture, we'll draw it again. Here's our detector or our screen. Here are the two slits or two holes. Okay, we're sending the electron out, but the electron isn't determined. It's like a ghost particle that is going through both things as long as we don't look at them, as long as we don't set up a detector here and try to see which one it's going through. So it's going through here, and it's what they're going to call a probability wave. There's a certain probability that the electron will end up here or here or here. And so it's like, as I said, a ghost particle that comes through both holes, and then finally, somewhere when it's going to hit the screen and we're going to detect it, it decides what path it's going to go on. And it hits the screen, and this probability wave collapses, and the particle is detected in one certain spot. But before that, you can't say where it is. That's what they're saying. That's the quantum weirdness. Yes? It shows up in different places and forms that pattern of light and dark lines. No. Okay. And so sometimes it'll go here and here or here and here. And they're saying basically the particle has a certain probability to end up at this spot and another probability to end up here. And so we'll look at it as a probability wave, like some kind of mathematical structure. And but we won't be able to say where it went through, which slit it went through. Okay? But if we close one of the doors, then it'll know that we're trying to watch it. And it will collapse, and it'll go through here, and it will make that one line here. But if we open the other door, then it's going to be sneaking through both doors as long as we don't look at it. And if we don't look at it, then it's like the story on those pages about Schrodinger's cat. As long as we don't look, the cat's both alive and dead. But if we look, we force the probability wave to collapse, and the cat is going to be either alive or dead. Got this now? Okay. I'm glad you do, because I don't. Okay, I'm going to read you a little more of this, because this is important. This became, and still is, the most popular explanation physicists give of quantum theory. All right, let me read you a little more. It's as if a myriad of ghost or potential particles become one real particle with the collapse of the wave function caused by our act of observation.
and we'll quote from John Grimman again, "What's worse, as soon as we stop looking at the electron, or whatever we are looking at, it immediately splits up into a new array of ghost particles, each pursuing their own path of probabilities through the quantum world. Nothing is real unless we look at it, and it ceases to be real as soon as we stop looking." So, what do you think? Now, I want you to think about this a minute, because this is important, because first we have to see that it is really weird, okay, like they're claiming, and then we have to see what it implies from what he's saying when he says nothing is real unless we look at it, and it ceases to be real as soon as we stop looking. Well, what do you think about that? Is that true? Is that true to your experience? If I walk out the door, have I stopped being real? Are you sure? It's like the old story of when the tree falls in the forest. Did it really fall if there's no one there to observe it? What do you think? Unless we're observing it, the universe becomes a series of potentialities, okay, possibilities. And when we observe it, it decides that it's going to be one particular thing, this thing and that, or that thing. But before that, it's not. That's like, we'll go back to the story of the cats, okay? Before we look, you can't say that the cat is alive or dead. Yeah, now see, the physicists are left with trying to take their mathematical formalism, their mathematical theory of quantum theory, which works and has many even practical effects, designing certain kinds of electronic equipment and everything like that. It's not a question of that it's a theory like an abstraction that may or not be true. From the point of view of the physicists, it's a very well demonstrated theory. But then they are trying to put together an explanation of what this theory means. And most of them will either not be interested in an explanation because they say, well, it works and that's enough, or they will accept this Copenhagen interpretation. Now I'm going to read John Gribben's passage again and see if we can extract a little more out of that, okay? The electrons not only know whether or not both holes are open, they know whether or not we are watching them, and they adjust their behavior accordingly. There is no clear example of the interaction of the observer with the experiment. When we try to look at the spread out electron wave, it collapses into a definite particle. But when we are not looking, it keeps its options open. In terms of Born's probabilities, the electron is being forced by our measurement to choose one course of action out of an array of possibilities. There is a certain probability that it could go through one hole, and an equivalent probability it could go through the other. Probability interference produces the diffraction pattern at our detector. When we detect the electron, though, it can only be in one place, and that changes the probability pattern for its future behavior for that electron. It is now certain which hole it went through. But unless someone looks, nature herself doesn't know which hole the electron is going through. All right, now, when they start talking that way, what's happening is they're taking a very definite philosophical position, okay? That the nature itself is indeterminate. That it's this fuzzy array of possibilities. Once you go below the level of the atoms and to the particles and you try to go below there, nature fuzzes out into this array of possibilities. Heinz Pengel, another physicist who's tried to write about this, says this: this indeterminism
was the first example of quantum weirdness. It implies the existence of physical events that were forever unknowable and unpredictable. Not only must human experimenters give up knowing when a particular atom is going to radiate or a particular nucleus undergo radioactive decay, but these events are even unknown in the perfect mind of God. Okay, so what we have here is a very definite kind of philosophical interpretation of what quantum theory means. And because most physicists will ascribe to it in one degree or another, as I said, then we're left with, well, what are we going to do about this? How compatible is this kind of theory with the way we see the universe as Christians? Are we going to build our theology on the basis of these kinds of what are supposed to be scientific insights? All right? Are we going to build our theology on what this kind of quantum strangeness is? Perhaps some of the process theologians are heavily influenced. I don't know that for a fact, but they could easily be heavily influenced by this view of science. There are certainly other Christian philosophers and theologians who have accepted this as some kind of demonstrated scientific theory and have then tried to build some kind of theological consequences upon it. But that's very rough going. They will say things like, maybe the way God treats matter, like this array of possibilities where nobody knows where it's going, is the way providence works in the world, or things like that, but they remain rather vague kind of statements. We're up against another situation where we're not dealing with physics itself, okay? The quantum interpretation is not physics itself. It's not that mathematical formulation of quantum theory. It's already an interpretation of what that means. That distinction will allow us to say, maybe this is not true. Maybe this kind of formulation is not true. All right? Now, this is a tough kind of issue to deal with, okay? Because we're not physicists and we're trying to, cope with this, but it's similar to those passages we're reading this morning, where we read these things, and these are what you would read if you were to read an account of the history of quantum theory. And there's many nice, well-written accounts about it. Very exciting time. But this is what you end up reading about. The two-slit experiment and the ghost particles and the probability waves and the fact that nature itself is indeterminate. Okay? If you, let's see, do you want to have those pages? I think I brought mine. Anyway, I want to read you another thing because it illustrates the way physicists think. Okay? And they have I think they have a lot of fun doing it. And I don't know that they take themselves always as serious as we tend to take them. On page 2, if you have it with you, or otherwise I'll just simply read it. There's all these possibilities, all the different paths the particle can take, okay? And they're saying then that we don't know which path it's going to take until we observe it. Well, there was a physicist, Hugh Everett, and he said, well, I have another way of solving the problem. Instead of saying that the probability wave collapses when we observe something, and therefore we know where the particle is, or we know whether the cat is dead or alive, I say we can solve the same problem by saying the universe forks every time one of these decisions takes place. And so, in the case of Schrodinger's cat, when we look, immediately another universe appears alongside the one we have, and in one universe the cat is alive, and in the other universe the cat is dead. You see? It just depends which universe we're in. And we say, what are these guys talking about? Well, who answered? All right, so is that a good theory? Why is that theory, if though it's a marginal theory among physicists, why do they entertain it at all? I mean, doesn't it outrage your common sense that every time there's some kind of decision, another whole universe pops into existence? Or you like that? Now here's how it developed further with the physicists. They said, and there's no way you're ever going to get beyond this enigma. And so there was a famous mathematician who wrote, called von Neumann, and he created this theorem that demonstrated, he felt, that it was impossible to get deeper than this in analyzing the problem. And that reinforced the physicist's viewpoint that this is what we're left with. No way to kind of sort it out and decide what's coming from the observer and what's coming from what's observed, and figure out what's really going on there. Okay, now let's get back to the many universes. So are you happy with the many universes? Every time we look, another universe gets created. Why would the physicists entertain this? No, I don't. Yeah, because what's happening is they're looking at the mathematics, and the mathematics allow you to solve the problem that way. In other words, you can take the same mathematics and you can say many universes are created at each juncture where, so the probability wave doesn't collapse, it simply splits off and you have both things. The mathematics allow it. Common sense maybe doesn't allow it, but that's not what they're talking about. And my point here is that they're talking about a highly mathematical, and this was the most highly mathematical aspect of physics up until that time. If the mathematics is good and the results come out correctly, then it's fine from the physicist's point of view. But we want to know, and deep down they want to know, what's really going on. And in this kind of presentation, they're not helping us very much. They're saying, oh, this is very weird and this is what we're left with. But they're already creating a interpretation of this mathematics. Does this make any sense? And I agree with you. You put it very nicely. Because they are like guys in their sandbox and they're having a good time. Because it's sort of like when you're doing that highly mathematized physics, you're playing. Okay? And the guy is sitting in his office with his feet on his desk and he's gone. He's away doing this. It doesn't mean there's no connection with reality. There is. Okay? But as you're saying, he's playing, he's putting together this theory, and he's trying it out, and he's amused, and yet we are misunderstanding the import of it, and the media doesn't help because they want pronouncements. So they get pronouncements, and we restore some of them. But that's not really what's going on. We can't do that. Okay? If we were to try to build our theology on quantum theory, like a couple of people have tried to do, or make stabs, it really doesn't go anywhere. It just bogs down into a lot of confusion. Now, it's all right to feel uncomfortable about this, and Einstein did not like this. Okay? He didn't like this. He was a more realistic person. And so when he was writing, at one time he wrote to Max Born, who was instrumental in creating some of the mathematics involved here. And he said, quantum mechanics is certainly imposing, but an inner voice tells me that is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice. He's talking about his idea of God, okay? So he's saying, I don't like this. This doesn't make me feel comfortable, and he made a number of efforts to try to overturn it and was never successful. I was saying that Einstein didn't like this, and towards the end of his life, there was a young guy, his name was David Bohm, who was teaching at Princeton, and he wrote a quantum theory textbook. This was in the early 50s, where he explained in great detail about this theory. So he understood it very well. And he sent a copy to Einstein, who was living at Princeton. And Einstein invited him over and expressed his concerns about this just didn't sit right with him. And he encouraged Bohm to try to figure out another way of looking at this. And Bohm did. And he actually came up with one way. Didn't exactly please everybody, even Einstein, but he started it in the early 50s, and he spent the rest of his life at different points developing it. And he came up with a very interesting answer that to the two-slit weirdness. And it looks like this. Okay, we've got our screen, and now you gotta pay attention to this explanation because it's so simple it can slip by us. It really can. Okay, here's the gun that shoots out the electron. Here's the electron. Bohm says, inasmuch as it's a particle, it goes through one slit or another. Okay? No doubt about it. But with this particle is like a field. Let's draw it like this. And this field accompanies the electron. And so the electron itself, let's say it goes through here. Okay? But the field that surrounds the electron goes through both slits. And it's this field that steers the electron to go to a different particular place. So that you have both the particle and this special field. And it's not the particle being a ghost particle going through both slits. It's a very real particle, but it's connected. It has this field connected with it, and the field goes through, and it's as if the field, which you could liken to sort of like a wave, makes the interference pattern and steers the electrons to the different places, and you end up with that interference pattern. Okay? Now all this looks like a simple answer, but this field has one striking quality. This field has the property of non-locality. And that's what we're going to talk about in the third part. This field sort of knows whether the slit is open or not. It knows if there's some measuring apparatus there. It's aware of distant features that are far distant from the actual electron, and somehow these distant features affect where the electron goes through this field he called the quantum potential. Okay? So there's none of the quantum weirdness when you do this. But we've replaced the quantum weirdness with the question of non-locality. Locality simply means that in the world of the physicist, it's, for example, here's one table, and there's the table where Tom is sitting, and there's no way that this table can influence that table at speeds in excess of the speed of light, which is like the cosmic speed limit. Okay? And so the sun's light rays come to the earth, but it takes maybe, I don't know what it is, 9 minutes or something to get here. And there's no way that an influence can pass from the sun to the earth quicker than the rays of light come here. Okay? But as we get into non-locality, it doesn't seem to obey that kind of fundamental law. And so we're dealing with a very strange kind of physical phenomenon that leads to all sorts of interesting questions. Basically, the way physicists do, he took the same mathematics, but he had more of a realist streak and more of a, common sense realist and almost a philosophical bent. And he didn't like this fuzziness of the quantum world, because he says, we really want to know what things are really like. Nor did he like this thing of von Neumann, the mathematician, saying we couldn't get any further down there. He said, I want to really know. And so he proposes this as a very real particle with a very real field. But it turns out that this field has this very strange quality. Right. So we have a little taste of it. And again, the lesson is not that we have to become quantum physicists, but it's just that we'll be a little more critical when we run across these ideas. And as Philip is saying, we can run across them a lot these days. Quantum this, quantum that. It's like some little slogan you put in your logo for your business. Quantum chicken, quantum whatever. But we owe it to ourselves. As Dennis was saying, that the physicists are having a good time, but well, as a physicist, for physicists, the actual formalism is very practical reality. Like I said, it's sort of like it's very practical reality, but it's when the theologians get their hands on it and kind of they think they want to make something big and momentous out of it, and it's not clear what they can do that way. I mean, there's a general sense that, and this is how we'll end, there's a general sense that some of you mentioned from this morning's discussion about this kind of mysterious interconnectedness of the universe, which is a very attractive idea, okay? It's a wonderful idea. But again, we can't just reduce it to this formless kind of mush and pretend we understand it. We have to try to get at it and then see what it's really saying. Okay? So we'll go on and talk about it in terms of this mysterious interconnectedness they call non-locality. The physicists do. Next time.
Okay. So let's just recap where we've been. First we're talking about the difficulty in taking modern physics and directly building some kind of theology or spirituality on it. That's point one. Point two is, even among the physicists, while they may agree about the math, they don't necessarily agree about the interpretation to give it. And our case was the difference between this Copenhagen interpretation and David Bohm coming up with a much simpler, more intuitive answer to why things happen as they do in the two-slit experiment. And so Bohm said he wanted to try to understand what this could possibly mean for our view of the universe. Okay? Does anybody have a question about that or want to ask a question about just what they're meaning by non-locality? I know it's difficult to grasp, but is it clear enough? Or do we want to, talk about it some more? It's simply meaning this when John Stuart Bell wanted to explain it, he used the case of identical twins that are reared apart. If you've read any of those case studies, they're fascinating, and they've been doing a bunch of them at this university in the U.S. Two twins are identical twins, they're separated at birth, and then 30 years or 40 years later, they're brought together. Well, we assume that they're going to look alike, and they do, of course. But it turns out that they're meeting for the first time, and they may wear the same kind of shirt, or their wife's name is the same, or they both have the same kind of dog and called it the same thing. There's like these uncanny coincidences, and not just in one case. Okay? All right, so they both have, a dog named Pal or something, or some exotic name. How do we explain that? That these two twins that weren't in contact will have these things, identical things that in no way seem to be genetically linked. Is it genetically linked, what you call your dog? Or, it doesn't seem to be. So how could we explain these uncanny coincidences that come up? I don't know that anybody has given a good answer. But this is a demonstrated fact. It's fairly well documented, and there's lots of cases, and I found them fascinating. Anyway, John Stuart Bell is saying something to the effect that, look at the two particles. They somehow know what the other particle is doing, and yet we can't figure out how they know it. They're acting in concert. Change one, change the other. But they're too far away from each other to think that a signal has passed from one to the other following the normal laws of physics. And so the physicists, as I said, don't know what this non-locality really means. Sometimes they say, well, maybe something going faster than the speed of light, but they don't like that because that's too many headaches. So they don't know. And so they're saying there must be some mysterious bond. Now, David Bohm, who had more philosophical bent, made several attempts to try to figure it out. He would say things like, well, we conceive of the universe like a lens, an optical lens, and the image you get from an optical lens, there's a point-to-point correspondence between the lens and the image. The top part of the lens mediates the part of the image, and the other part. But then he says, but it looks like the universe is not like the lens, but it's like a hologram, where each part of the hologram, if you were to kind of break it off, contains in some way the whole image. Okay? It's one of the properties of a hologram to do that. And he gives another example. He says, imagine taking a cylinder, and there's a bigger cylinder that's on the outside of it. And in between we have some kind of viscous liquid, some kind of thick, sticky liquid. And we put a little drop of ink in that liquid, and we turn the outer cylinder so the little drop becomes pulled out into a thin, thin line that gets thinner and thinner until it disappears. If we reverse the process, then we'll gradually see the line, and then we'll see the dot appear. The point he's trying to make is that what if there were a richer matrix beyond the three-dimensional time and space that we know? What if there were, here's time and here's normal space, but what if there was some kind of, call it a shortcut that connects the two? Call it whatever you want. Sometimes the physicists use this idea in another context, and they claim that one part of the universe is connected with another one by some kind of little wormhole. But in this case, what Bohm is trying to do is say, what if there is another dimension that's not limited to space and time like we know it? He gives a good example. This one's my favorite. He says, imagine a tank, and in the tank is a fish. And on one side of the tank, we've mounted a camera, and on the other side, we've mounted another camera, okay? Now, that would mean we would get two images, one from one side and one from the other. And we could make a big problem out of saying, well, how do we relate these two images? Just like we make a problem of how can we relate these two particles. But in the case he's given, it's not really a true problem, because there's a higher dimensional fish that is giving rise to the two-dimensional images. In other words, there's two different kinds of two-dimensional images you're seeing on your two screens. And you're seeing these images move in different ways. But if you realize that they're just reflections of this three-dimensional fish in the tank, then all of a sudden the problem resolves itself. We understand where the two images come from and how they're related to each other. Well, Bohm is suggesting that these two particles are like the two images, and maybe they're connected in some higher dimensional reality. This is a reality he ends up calling the holo movement. And he waxed kind of philosophical, trying to explain what that might be. But for our purpose, we're left with this kind of very suggestive result, that physics seems to be pointing now to the fact of non-locality. It's not like, it's very difficult even for the physicists to talk about what that might be, but it seems a suggestive thing, and it has been based on a certain amount of experimentation. And people have tried to squirm out of talking about non-locality, but what they've done to do it seems, get you in worse problems. All right, so here we have a result that may be very interesting for philosophy and theology to try to reflect upon. It's going to be a tentative thing, just like it's tentative even with the physicists. But what does it suggest to you? Does it suggest anything if this turns out to be a fact? The question would be, is there any way out of the resources of our own tradition of philosophy and theology that we can understand how the universe could be interconnected like this. It's similar to the way sometimes we understand spiritual presence that doesn't take place through space and time. But if we start looking at this, then the universe, instead of being laid out flat on a table, so to speak, into all these little sectors, and so that one is far away and this one is close, and it's all laid out in space and time, it begins to gain a certain depth if it's somehow interconnected at a deeper level. Yeah, well, it certainly seems to reflect kind of that there are more connections than simply the kind of push and pull mechanical connections that connect things, which is the way physics was going for a while. Let me tell you a couple of other examples that get us outside the field of physics, but I think are interesting. You can see similar ideas appearing in the field of biology. One example, for example, there was this South African naturalist who he took a termite nest, and those are sometimes very large mounds, and he took a steel plate and he drove it through the nest, so he broke the nest into two parts. And he naturally caused a bunch of damage doing that. And then he watched and he saw that the termites working from either side were rebuilding the nest and building these tunnels and arches, and these arches were meeting. Okay? And so he had to ask himself, how were they communicating? If they could do this while the steel plate was there. There was some kind of mysterious kind of intercommunication beyond the normal level. Another example from the biological field, there was a biologist, an embryologist called named Hans Reich at the end of the 19th century, and he was pretty much a materialist like many other biologists of the time. And he started to do experiments with sea urchins, where he would take the embryo of the sea urchin and some way slice it in half or take part of it out and remove a whole hunk and then watch what happens. And now, on the basis if that organism was simply a machine, so take your machine and chop out a big hunk of your machine, it's not going to work. But in this case, the little embryo would reconstitute itself and end up, in many cases, forming a complete creature, although of a smaller size. So there was something there beyond what you could call the mechanics to allow it to go through that process. Another example from the field of psychology. C.G. Jung, in his practice, would began to run into these cases of what he felt were uncanny and meaningful coincidences. One of his favorite stories was he was treating a woman who was had a very rationalistic cast of mind and was sort of out of touch with the deeper parts of herself. And he wasn't making a lot of headway. And one day she came to his office and she told him that she had had a dream. And in the dream, she had dreamed of a beetle, and with imagery that suggested it was like one of these deep archetypal dreams of the scarab beetle that appears in a lot of Egyptian myths and is connected with stories of rebirth. The beetle in the Egyptian myths is pushing like a ball of dung, which represents the sun, and so forth and so on. Anyway, she's telling him this dream. And while she's telling him the dream, they hear this tapping at the window. And Jung goes over and he opens the window, and in flies something. He grabs it in his hand and he holds it out to her, and it's a beetle, which was the closest Swiss equivalent to that scarab beetle. And he says to her, "Here is your beetle." And that had the effect of breaking through that shell she had built up between her and the depths of her personality. Now, Jung eventually ended up calling this synchronicity, which is now a kind of a buzzword, but it simply meant there is no obvious causal connection in the sense of efficient causality between her dreaming the dream and the beetle appearing. You can write it off as pure coincidence if you want, but there are any number of stories fairly well documented of the same kinds of meaningful coincidences. Okay, so my point is simply this. What the physicists are discovering with non-locality, the biologists have their own version, and so do the psychologists. There's like these connections between people and people, people and animals, people and nature, nature itself and its various parts that go beyond the kind of understanding we have through the as far as the sciences can determine at the moment. And this is what has led some of the better people in those fields to get a sense of a more holistic and interconnected universe. So, how about some questions? The physicists have actually thought about that, whether you could take this fact of this non-locality and this interconnectedness and somehow use it to set up some kind of communication system, for example. But they have rather involved explanations why they don't believe that will work, even though they're interconnected. I couldn't spell it out for you, but most of the time they conclude that it's not possible to control it. It's as if these two things will agree, but they will agree in a random pattern, so that sometimes they're heads, but not heads, tails, so you could use it, but heads, both heads 3 times in a row, tails 7 times in a row, heads, tails, it's a random pattern, and yet it's still agreeing. That's basically what I remember them saying. So it's going to be tough to use it that way. It's going to be tough to use it that way. It's the same kind of thing, because now you're getting into a thing of like extrasensory perception. If you believe that it exists, you may see it to be similar to like Jung's synchronicity or some kind of interconnectedness that doesn't depend on the normal modes of communication. And lots of people have had experiences that just are uncanny that way. But it'll be pretty hard if you decide you're going to beat the telephone company by sending messages that way. Even the people who have claimed to be psychic, it's mixed up with other things in the psyche and it's never that clear. So you couldn't, set up your own little message system very well that way. I think it's the same. There's problems doing that, but it is a good question. Yeah, and there's a English biologist, Rupert Sheldrake, who has taken and developed these ideas in a biological sense. And it's interesting that he did this, wrote one of his first books while he was staying in Shantivanam with B. Griffiths. And when he published this book, there was a real violent reaction from some of the established biologists, because they simply didn't want to hear about these kind of things. But he has made a very persuasive case in a series of books about what he calls morphogenetic fields as well as morphic resonance, how things affect each other beyond the normal mechanisms of biology. And it's very much like our own tradition of things having souls, like we used to talk about animal souls or vegetable souls and human souls and so forth. And I think there's a bridge that can be built between our own notions from our own tradition and these ideas. Well, that's interesting because Jung tells a similar story. And the story goes that there was this husband and wife, and the wife believed that at the time of the death of certain of her relatives, birds had appeared and appeared in the neighborhood and come around her house. Anyway, they go to Jung and they're talking to him because they think there's something wrong with the husband. And then they're wondering if it's some kind of heart condition. So Jung sends the guy off to go to the heart doctor. And the guy goes to the doctor who examines him and finds nothing wrong. And his wife is at home. And he comes out of the heart doctor's office and he collapses on the street and he dies. But while this is happening, this flock of birds has come and have sat down all around the woman's house. So she had this premonition that death was about to take place. Now, what do you make about this? We could rub it all out, but you're left with the strange sense that there's something there, even though it's very difficult to get at it. That's a good point because Jung claimed that it was in the situations of great stress or emotional upheaval that these kinds of events took place. It's like this deep activation of the psyche was connected with these synchronistic events taking place. When Jung tried to think about this idea of meaningful coincidences, he tried to trace it back into history. It turned out before the rise of modern science with its kind of more rational mind, people accepted that there was a certain kind of correspondence. Man is the microcosm of the universe, and a correspondence theory between what happens in heaven and what happens on earth. They're all kind of, maybe we would say, vague theories or something, but there's this whole perspective that the human race has had for a very long time, that there are these correspondences. And now the scientists are bumping up against their own versions. One of the examples that Sheldrake, the biologist, uses is he says that it seems to scientists that one scientist is trying to create a certain kind of crystal or synthesize a certain kind of reaction. But once the first guy does it, then it somehow seems easier for people in other parts of the world to do it. Not just simply because they've told them about it. And people have had all these strange theories. It's like this crystallization thing, that the first guy struggles to create the crystal, the new crystal. And so they have, the scientists are saying, well, maybe one scientist went there and he got one of the little fragments of the crystal in his beard and he walked over to the other lab and here. But it seems like there's some kind of this is what Sheldrake calls morphic resonance. And he actually tried to create some experiments to demonstrate whether this happened or not. I'll get to that in a minute, but another example he used is that in England, one of their birds, I think it's sort of like one of the little birds learned how to peck through the cardboard tops of the milk bottles and drink the cream, okay? And so in one limited area this was taking place, but all of a sudden it seemed to explode, and all the birds of that species all over England were doing this at a rate that was beyond the normal rate of propagation of the birds kind of moving from one area to another. So it's like weird, okay? Well, it's like how did the other birds in the other part of England learn how to do this, since they didn't it doesn't appear like they didn't see the birds do it. Let me just describe one experiment that people have tried to validate Sheldrake's ideas about this idea of one person does it, then it's going to be easier for the next guy to do it. Or if, put it more exactly, if a lot of people are doing something, then it should be easier to learn how to do it for someone else than if it's some new thing that only a few people have ever done. So what they did was take a well-known Japanese nursery rhyme, and then they made up a nonsense thing in Japanese that didn't make any sense, and I think they even made a third of Japanese words, but it wasn't a nursery rhyme or any known thing. And then they had people try to memorize these three different things to see which one is going to be easier. Okay? And they did this with a whole bunch of people, and they showed that it was easier for people, non-Japanese people who didn't know the difference, to memorize the traditional Japanese nursery rhyme. But as they indicated, there was no way to really make an airtight demonstration that the nursery rhyme was not in fact simpler than the others. So, it's suggestive, but it's not, firm evidence. And in actual fact, we have a very well-developed philosophy and theology about that interconnectedness, which I'm sort of taking for granted here, but maybe has fallen a little out of our normal sight. But there are some very beautiful things that have been done to show how interconnected we are, just by the fact that we share the same human nature, and then how intensified this unity is by the fact of our union in Christ. Emil Mersch, who was a great theologian in the 20th century, that was one of his favorite themes. And I actually ended up writing a book about a lot of that simply because it was such a rich kind of thing. So it's almost as if we could say there's this kind of spiritual interconnectedness and a philosophical interconnectedness, and now we're seeing that even at the level of the empirical sciences, they're demonstrating this kind of interconnectedness. So to sort of wind it up here, we end up seeing the universe not as some alien thing, but as we work through it, then we're going to get a perception of we have kind of emerged out of the universe and carry it along with us and inside us. And that's why these uncanny things happen in our relationship with nature and the animals and with each other. So it's like one, people are kind of trying to say one big organism, and in a certain way that's not a bad way of looking at it. One interconnected, and that's what the very word universe means.